Okay, so last time we learned about definite integrals, right? And we learned how to evaluate them at their boundary points. Today we're going to move on from that to the fundamental theorem of calculus, right? Okay, so the big thing here, right, is this. The big idea here is this. Suppose f is a continuous function. Then we knew, right, that capital F of x, we knew that this was the antiderivative.
We can't see the notes packet you're trying to show us.
And what about this? What about this? What did we say the integral found for us? What quantity do we find by the integral? What geometric quantity does the integral give us? Starts with an A, ends with an A. Area, right? Area under a curve, remember? So the integral gives us area under a curve. Okay, so what we see happening here is that the quantity area under a curve can actually be found using an antiderivative, right? That is huge. You don't have to find the area geometrically using trapezoids or rectangles. You can actually find that area using the antiderivative and evaluating at different points. I mean, that is huge. That is like the main idea of everything that we're doing here. And so now, the fundamental theorem of calculus says, if you take a derivative of both sides of this with respect to x, then what you have here is df dx, which is the derivative of the antiderivative okay? And here, if you take a derivative of an integral, then you end up getting back the original function. So saying that the derivative of the antiderivative is equal to the original function. Okay? So that is the fundamental theorem of calculus. Now, how does it all work? In order for this to work, okay, when you're taking the derivative of the integral, the bounds of the integral have to be so that this lower bound must be a constant, right? It has to be a constant, 0, -3, 4, pi, e, whatever. And the top limit must be an expression. It must include an x, right? It could be just x, or it could be an expression including the variable. And when I say x, like it has to have the same variable with, with which you are taking a derivative, with respect to which you're taking a derivative. Okay? All right. So bottom line, if we take a derivative of the integral, we get the same function back. But what happens? The variable is an x. Okay, so let's take a look at this for a minute. We have a couple of integrals here, and we want to find dy dx. Y is an integral. So dy dx is d dx of this integral. Okay? All you do here, because you're taking a derivative of the integral, it's like multiplying by 3 and then dividing by 3. You're sort of undoing what you did. All that happens is you get your original function back, except this variable is replaced by x. So 1 plus x squared. That's it. There is no computation whatsoever in that case. All right? So what about here? This is d dx, of the integral of negative pi to x cosine t dt, right? Always be careful that it is a constant at the bottom and then a variable on top. So you're taking a derivative of the integral. You don't take the derivative of cosine. You just say this is equal to the same function cosine with a variable of x. Okay? Questions? Matthew,
Never mind.
you sure? Okay. All right, next. Finding dy dx using the chain rule, right? That top bound doesn't always have to be just an x. It could be a function with an x. So now when we do this, right? Now when I take a derivative of this from 1 to x squared of cosine t dt, now what happens is, okay, that expression goes into my variable. So I have cosine of x squared. But remember, you're taking a derivative. And if you're taking a derivative, you have to take a derivative of the inside as well, right? Chain rule. So that means this now gets multiplied by the derivative of x squared. Right? So you get times 2x. Never forget that. Okay, so here, so that will be 2x cosine x squared. All right, let's do this one. d dx from negative 3 to negative 2x, u cubed minus 5 du. Okay, the negative 2x goes in here, so I get negative 2x cubed minus 5 times the derivative of this, negative 2. So finally, that's negative 8x cubed minus 5 times negative 2, 16x cubed plus 10. Questions? Okay. Now, let's take things up a notch, yes? What if you've got a rebel of an integral and the variable of in the bounds is in the bottom, not on the top? What happens then? So take a look at this. I want to take a derivative of this, but look, this time x is in the bottom and the constant is on top. You can't just say, oh, well, no, because in your theorem, right, like it's a theorem, it was defined as constant on the bottom, variable on top. This is what I mean when I say math is consistent, not like some other situations we've run into this week, right? So it has to apply in every single case. So what we do is we have to flip this thing around. So when you flip it so that it's 5 on the bottom and x on top, what do you have to do to this?
Make it negative.
Make it negative. And now you take a derivative of that whole thing. Okay? So that becomes negative. X still replaces all the variables. 3x sine x, that's it. Okay? All right. Here's another situation. Now I have variables on both limits of integration. Okay, that won't work either. I have to have explicitly variable on top, constant on the bottom. So I have to split these up. Well, okay, here's how we split it up. I have a 2x and an x squared. First, determine between the 2x and the x squared, which one is the smaller value, right? So it doesn't matter what x is, except when x equals 2. 2x and x squared, 2x is less than x squared, right? Right? Most of the time. So now here's what we do. What you want to do is you want to split these up. It doesn't matter at what point you split it up. So we say, okay, we're going to go from 2x to some constant, and then from that constant to x squared. So we're going to write this as 2x to some constant. Okay, what to make the constant? You can make it 5, you can make it a, you can make it whatever you want. The convention is to make it 0. It really doesn't matter. It's a placeholder. Okay, and then we have 2 plus e to the t dt plus 0 to x squared 2 plus e to the t dt. Okay, the point is though, I have a constant here and I have a constant here, right? That same constant. It's like a continuous thing. But now, right, one of these is still messed up. The first one is still messed up. So I have to flip it so that the constant is on the bottom. So I say negative 0 to 2x 2 plus e to the t dt plus 0 to x squared of the same thing. Okay, so now I'm ready to take a derivative. dy dx is negative, plug the 2x in here, 2 plus e to the 2x times 2, plus plug the x squared in here, 2 plus e to the x squared times 2x. Okay, so let's simplify some things. Just write it with the constants in front, and that's it. You're done. Questions? Okay. So guess what? Fundamental theorem of calculus comes in 2 parts. That was part 1. And now for part 2. Part 2, you've actually been doing it. You just didn't know that it was called Fundamental Theorem of Calculus Part 2. So again, the Fundamental Theorem of Calculus Part 2 says if f is continuous at every point, and if capital F is the antiderivative, then again, the area, right, the integral or the area from A to B is equal to the antiderivative evaluated at B minus the antiderivative evaluated at A. You've actually been doing this when you were doing definite integrals on the homework, okay? This used to be called the Fundamental Theorem of Calculus for Integrals, or the Fundamental Theorem of Integral Calculus. Now and then at some point it was called the Integral Evaluation Theorem. Now it's just Fundamental Theorem of Calculus, FTC for short. Okay, that's what we're calling it in the, in the 2000s. So it's FTC. Okay. All right. So let's do a couple. You've actually already, like I said, had practice with this, but these are a couple of other ones that are very common on like multiple choice tests. Okay, so this one, I take the antiderivative, so 4x plus 2x squared over 2. It went away. So divide by 2. All right. And remember how we would put that vertical bar, right? You could also, if you put it in brackets like this, that takes the place of the bar, and now we could just say this is from 4 to 6. All right. So the 2's here are going to go away, so I'm just going to make them go away. Okay, what we're going to do is we're going to plug in the 6. 4 times 6 plus 6 squared minus plug in the 4. And that's 28. All right, what about e to the x? Gotta love e to the x, right? Integral is just e to the x, -1 to e. So when I plug e, I get e to the e minus e to the -1, but we don't like negative exponents. So it's e to the e minus 1 over e. Okay. What about this one? This one's an interesting one. When I integrate, what do I get here for the antiderivative? Who can tell me?
X to the 4th over 4 plus x.
Yep, from -1 to 3. Okay, when I plug 3 in there, it's 3 to the 4 over 4 plus 3 minus -1 to the 4 over 4 plus -1 or -1. Okay. All right, so 3 to the 4 over 4 is 20 1/4 minus, so this minus 1/4, that's 20. Those two are 20. And then you've got 3 plus 1, 4, so that's 24. All right, so on a multiple choice, right, if something like this comes up, see if you could do, like the little combinations like that. Okay, this next one is also very, very common because AP wants you to be quick on your feet with radicals. So this one, right, it's x to the 3 over 2. If you add 1, you get 5 over 2. And now you have to divide by the 5 over 2, which means we just multiply by the reciprocal in one shot. And we're going to evaluate this from 0 to 4. So the way this is meant to be done is you take the 2 over 5 out, and now I'm going to plug in the 4. This is a radical, right? 4 to the power of 5 minus radical of 0, square root of 0 to the power of 5. Okay? So that's 2/5 times 32. Okay, 64 over 5. Questions? All right, next one. What's the antiderivative here? What do we get? Antiderivative of this. Matthew?
Oh, cosine.
Cosine of theta, yeah. Right, remember the negative is just part of it, right? from pi over 6 to 5 pi over 6. Evaluating they're both the pi over 6's, which means it's the root 3 over 2's, right, for cosine. 5 pi over 6 is in the second quadrant, so it's negative root 3 over 2 minus another root 3 over 2. Again, very common for multiple choice because it's simple enough, right, that it doesn't take too much time. But, you know, there is that added, like if you're not cautious, you know, how to add and so on. I bet you one of the choices here will be 0 because the student will be like, ah, yeah, they just cancel out, right? But it's negative 3. All right, next one, F. I'm gonna give you guys 2 minutes to do F on your own. But first, look at what that looks like, the integrand. It's x plus 1 squared. And we haven't learned how to do that form yet. So what would you have to do first here? Yeah.
Do you multiply it out?
Multiply it out. Exactly. All right, so 2 minutes. On your mark, get set, go. All right, so let's tackle this one. All right, antiderivative is gonna be what? Who can tell me? It's x cubed. Go ahead and yell it out. X cubed.
Over 3
Uh-huh.
plus x squared plus x.
Plus x. Awesome. From negative 1 to 0. So now, when I plug in my 0, right, I get 0 plus 0 plus 0. Minus. Now I plug in the negative 1. So I get negative 1 cubed over 3 plus negative 1 squared minus 1, right? Mind your negatives here. Negative. Okay, so this one is negative 1/3 plus 1 minus 1. The 1's go away, and I have negative of negative 1/3, 1/3. Okay? Tricky, because it's simple enough that any calc student can do it. And then it's like, okay, you know, like when you've got that adrenaline and you're rushing and you're stressed, you know, can you keep the negatives together, right? And it's usually a negative problem, this one, right? That gets you. And so, you know, in the choices, you will probably have negative 1/3, positive 1/3, you know, you will have, you know, the situation where, you know, that one is negative and, you know, see how it works and so on, okay? All right. Okay, let's move on to the last thing we're gonna do today, total area. All right. So we've talked about area before, and you remember on the quiz, right? Way back when in 2020, right? We had, oh, shoot. We had, you know, like cases like this, right? Or whatever, like something like that, where you had to find the area, right? And if I asked you to find the area from the beginning of this interval to the end of the interval, what would you do? You would find all these areas and then you would add the positive, but you would subtract the negatives, correct? Right? So part of the area would cancel out, okay? Now, what if I wanted you to find area but not have anything cancel? What if I just wanted you to find the absolute value of all of the areas added together, the total area, okay? So just the positives of all of these. What would you do then? Well, you wouldn't count anything to be negative. You would just, you know, add like 2 plus 5 plus 2 plus 1, right? That's what you would do if you had to do it geometrically. But what if you had to do it analytically? What if you just had a function and you had to do it, using the function? Well, here's what we do. We know that most of the time our graphs are not just going to be above the x-axis. Sometimes they're going to dip below. So to find the area in that case, you partition your graph with the zeros, you integrate over each interval, and then you add the absolute values. So the case we're going to look at is this, 3x squared minus 3, right? And we're going to go from -2 to 2. When you graph this from -2 to 2, this is what it looks like. So you see some parts are above and some parts are below. The shaded is the areas that we're trying to find, right? So this part here, this is -2 and that is +2. All right, so the way to find the area is, first you have to figure out the points where y crosses the x-axis. Okay? And you've been doing that since you were little. What you do is you take your equation and you set it equal to 0. So x squared is 1, x is plus or minus 1. So those are the points where it crosses below the x-axis. Okay, so to find this first area, right, or to find each of the areas, I need to integrate. So let's see, the total area here is the integral from -2 to 2, not of the function though, of the absolute value of the function, right? Because if I just do 3x squared minus 3 in the integral, it will do what we were doing on the quiz, subtract out the negative areas. In order to make sure I count all of the areas as positive, I have to put it in absolute values. So now, how do we do this? You partition it, right? And now I have 3 areas. Well, the first area here, the integral for that is from -2 to -1 of 3x squared minus 3 dx. Since it's above the x-axis, I just leave it as it is. It's going to be positive anyway. Plus, now look, the second integral is from -1 to 1, 3x squared minus 3 dx, right? But now, that green integral, the value of that is going to be negative if you do it by hand. Just like we found, like negative answers on top. The value of that is going to be negative. However, because I want to count it as positive, I put absolute values around it. Plus, the last area, I just take it as it is. Okay? Now, what I'm going to do here, what we're going to do next is we're going to find each of these, we're going to evaluate each of these integrals separately. So you see how here we evaluated integrals? We're going to do that 3 times here. But that takes too much time, and I've already done it. So I'm going to tell you, when you evaluate the first one, right, you get 4. Plus, the second one gives you -4, rightly so, because it's underneath, but it's in absolute values, plus 4 again. All right, so together, that is a 12.
Wait, why is it absolute value?
Because we don't want it to count as negative and cancel out. We want to find the total area. We want to find the absolute value of all the area. Okay? All right. To do it with your calculator, you just plug it in with an absolute value. So what I'm going to do here is I'm going to show you both versions of this. So to find the integral, right? It's that button right there. And we're going from -2 tab to 2 tab. Okay, look, if I just do 3x squared minus 3 tab dx, right? If I just do 3x squared minus 3 dx, look at what I get, right? I get 4. Why? Because it counts this without the absolute value, right? And it cancels out, so I get a total area of 4. But that's not the total area, right? That's only 1/3 of it, as you can see. So what I need to do is I need to put this in absolute value. So I'm gonna do Control X, delete it. You guys know you can do Control X and Control C and Control V on these, right? On your calculators. Okay, absolute value button is here. Control V. So now when I put it in absolute values, I get 12, right? Because it does in the background what we just did, and it does it like separately. Okay? All right. Questions? Okay, so that is section 4. That's the end of this section. The homework is from the book this time, right?